Okay, thanks, Ruben, for introduction. He already says everything that I want to say, that I use periodic uniform magic product states to extract universal data of critical quantum spin chains. Okay, so just for those who are not familiar with this topic, let me introduce these terminologies one by one. So critical quantum spin chain, right? It's a quantum spin chain at its critical point, which means the second order or higher order phase transition point. As you know that the critical phenomena is universal, which means that there are many lattice realizations that could lead to the same long range behavior or long distance behavior. And this long distance behavior are called universal. And in order to characterize this long distance universal behavior, we need the universal data. And this is an example of the universal data, which I will mostly talk about. So if you don't familiar with it, that's fine. I will introduce it later. And then a periodic uniform magic product state. It's just a tensor network state like this, which consists of one single tensor A. And it's just a numerical method, and I will not go deep into it. And the periodic uniform magic product state is just a way to diagonalize the spin chain. Okay. Okay, let me be in a very high level to introduce what I have done. So this is a collection of many works. So I will just sketch the surface to give you a broad idea. So let me start with the critical quantum spin chain, which is very important that it is periodic. So this gets rid of boundary effect. It's more clean. If you have boundary CFT, that's more complicated, and we just don't want it. Okay. For example, if I have a critical Ising model look like this, and I want to know what's the universal data that captures the phase transition. Okay, so the way that we did that is based on the low energy eigenstates of the Ising model. What do I mean by low energy eigenstates? So first, this Hamiltonian is translation invariant, and we put it on periodic boundary conditions, which means that momentum is a good quantum number and momentum is quantized. So if you plot the low energy eigenstates, the energy versus momentum, you will get the figure in the downside. And for example, like this is the ground state. The first state is the ground state, which we shift to energy 0, and of course it has momentum 0. And the second state is the first excited state, which also turns out to have momentum 0. And you can build, you can see the structure of this energy versus momentum spectrum. And interestingly, you see that there's an interesting tower structure in this spectrum, and this is really the whole thing. What the whole thing is about. That how we can exploit the tower structures in this figure. Okay, on the right-hand side, we list a number of universal data that we can extract from this low-energy spectrum, which includes a set of primary, all the primary operators and conformal towers and central charge and OP coefficients and so on. Well, for those you don't know about CFT, that's fine. Like you take this as numbers, which describe the universal behaviors of the critical quantum spin chain. The 1, 3, and 4, which means primary operators, central charge, OP coefficients, are what we normally call conformal data, and they describe, they completely determines the CFT, which means that they completely determine the long distance behavior of the quantum spin chain. There are other things which are interesting also, which are conformal towers and emergent symmetry, if there's any, apart from conformal symmetry, and also the entanglement properties of the CFT. And of course, this could, in principle, be derived from the conformal data, but still it's sometimes interesting to also exploit them, try to see them directly. Okay. Okay, so let me say something about CFT. On the left-hand side, we have the Ising model. And on the right-hand side, we have the Ising CFT, the spectrum of the Ising CFT. So let me tell you what the dots means here. So here, the x-axis is the conformal spin, and the y-axis is the scaling dimension. So whenever you see a point there, it means that there's an operator in this CFT which has the following scaling dimension and the following conformal spin. So for example, in the CFT, you see that there are three colors, right? There are three colors in this figure, and each color is known as a conformal tower. So let me take the orange one, for example, right? So you have at the base sigma operator, which is known as the sigma operator. It has some scaling dimension, some conformal spin, and then you have a bunch of operators which organized as a tower structure, and this goes infinitely up, and this and this gives you one conformal tower of the CFT. And of course, you have in the case of Ising CFT, it's known that there are also the other two, which is known as the identity tower and the epsilon tower. Okay, and the whole thing of this talk, if you don't remember anything, is that the left hand is roughly equal to the right hand side. So this is extremely important. Okay, so based on this roughly equal sign, we can read the right hand side from the left hand side. And of course, you see that the left hand side is not completely equal to the left hand side. That is because it is working at finite sizes. So usually when you have a finite size quantum spin chain and a continuum description, there's always finite size corrections. And it is generally known that large size makes better approximations. Okay, so so this is the first observation, and the second observation of what we did is that on the right hand side, the operators with the same colors, that is the operators in the same conformal towers, are connected using the Virasoro generators. And can we do the same thing in the left-hand side, right? If we can do it, then that's perfect. Because we can know that which states correspond to which state on the right-hand side without guessing. The rough idea is that we can construct lattice operators that act as Virasoro generators for the low-energy eigenstates, which means that we can also construct operators that act as these arrows on the right in the left. Yeah, and this will enable us to know which state is which in the CFT. I will be more precise later. Okay, so this lattice Virasoro generators will enable us to know which are the primary operators and what are the conformal towers, and also turns out it will also give us a central charge. Okay.
Yijian, hello. That's a quick question. So on the left, which level did you take to scale the plot? You chose one of them to make the scaling work? In the
yeah. Just maybe you can just fix fix the energy of this state to be to be one is. But yeah, but I will be precise about the scaling later. Okay.
I have a question. Quick question. On the left-hand side plot, you've calculated the spectrum at the critical point?
Yeah.
Okay, thank you.
Okay. Okay, so we can actually do more than connecting states within a conformal tower. We can actually do something like connecting states with different conformal tower, as we show on the right-hand side. So this is this arrow and this arrow. On the CFT side, this arrow can be achieved by applying a primary operator on the operator, and this is of course for those who know about CFT, you know that this is a result of the fusion of operators in CFT, and this turns out to be governed by the OP coefficient. And it turns out that on the lattice hand side, we can do the same thing. We can construct lattice operators that act as primary operators in the low-energy eigenstates. So, for example, on the left-hand side, we can construct lattice operators that has the same arrows, which gives the same amplitude as the right-hand side. And of course, still, we should know that large sizes make better approximations. And from this procedure, we are able to extract even more conformal data that I think is unprecedented, which we can compute all the OP coefficients and also try to see if there is any emergent symmetry. For example, the Kac-Moody symmetry of super Virasoro, that is what this J and G means. But if you don't know it, that's fine. Okay. And okay, so we want to go to larger system side because as I said before, larger size makes better approximations. And so here's the technique. So we make a technique which we can compute low-energy eigenstates for up to like roughly 200 spins. It could be more than 200 if you have more computational resources. And this will give us a much more accurate conformal data than before. These tensor networks are technical details, and I won't go into details in this talk. Just let me say that the cost of the whole procedure is proportional to the number of spins, and also is polynomial in the bound dimension in these tensor network answers. And to give you a hint, if you have 64 spins for the Ising model, it just takes you 5 minutes to get the whole bunch of ground state and low-lying excited states. And for 256 spins, you need larger bound dimensions, and it will take longer, but still affordable. Yeah, of course, for more complicated models, the time will be longer, but this is a significant boost. Okay.
Can I ask a quick question? I know you said you don't want to talk about the technical details here, but just one quick question out of curiosity. Do you have a sense of a canonical form for this ansatz? Or is there?
No.
Okay. So you have to do all the contractions exactly, like literally.
Yeah. So this is why this is 5, not
okay.
3. So if you are familiar with BMRG, you know that it's 3. Yeah. In this case, we don't have a canonical form, so it's 5.
Okay, thank you.
Okay. Okay. So so the last thing that we can compute is the entanglement properties, which is very hard to compute exactly if you're working with field theories. And also, these entanglement properties are very important in holography because they conjecture that this is something due to the bulk ADS space. And in this talk, I will just focus on a multipartite entanglement measure, which is known as the entanglement of purification. And this is very hard to compute in the field theory, and I don't know anyone has computed that before using exact method. So at best, we can compute it numerically. And in this work, we compute entanglement of purification for a generic lattice model, which can be described by a free CFT or interacting CFT. So it will be a very challenging problem to solve and also very interesting. Okay. Okay, so that is the overview. Let me go into a little bit into details of how each of these is done. And just let me step a little bit into detail about the CFT, right? So I mentioned about this conformal data, right? So let me take the Ising model for an example again. Yeah, so for the Ising model, the conformal data first consists of a set of primary fields, which there are 3, and we call it identity, sigma, and epsilon. And they all have conformal spin 0, and they have some scaling dimensions. And as you can see that the spectrum is organized into towers, and at each towers you have scaling dimension differ by integers. Right, so if you look at the green dots, and they have 1, 2, 3, 4, and if you have the red dots, you have 1s, 1 plus 1s, 2 plus 1s, and so on. Okay, so this is one part of the conformal data, and this one part of the conformal data determines 2-point correlation functions in the CFT. Okay, And in order to compute higher order point functions in CFTs, you need additional information, which is fusion of operators. So in general, if you have two primary operators, you can fuse them into a sum of primary operators and non-primary operators. And in this equation, I just showed the primary operators. Okay, so this is governed by the OP coefficient. By this, you can try to simplify the higher order correlation functions down to two-point correlation functions. And the two-point correlation functions are determined already by the conformal data, by the scaling dimensions and conformal things. So that's why the OP coefficient is also very important. And the last thing that is important is the central charge. Why the central charge is important is that the central charge will typically come into also come into this expression, and because this expression also have a plus dot dot dot, so central charge will come there. And typically the central charge is the only thing that determines the properties of non-primary operators. So if you have primary operators and the central charge, you know everything about non-primary operators, and then you need the fusion rules to compute all the higher point correlation functions. Okay, and for the Ising model, this is exactly solvable, the C equal to 1/2, and there's only one non-trivial OP, which is sigma sigma epsilon. Of course, by non-trivial, I mean that not contain identity. If you have identity that is identity fused with anything, it gives you that thing itself. So non-trivial means sigma sigma and can fuse to epsilon, and sigma epsilon fuse to sigma, and this gives you the coefficient 1/2. And this is the set of conformal data that we want to determine. Okay, let's see first how to extract scaling dimensions and conformal things. Okay, as I mentioned before, the whole thing of this talk is about left-hand side, which is lattice eigenstates, roughly like the right-hand side, which is CFT eigenstates. Of course, I am playing a game here, which I exchange CFT operators for CFT eigenstates. And this is legitimate because for all the operator state correspondence. So the right-hand side is the operator spectrum, and it's also the state spectrum. And that is just to be comparison with the left-hand side, because left-hand side is also state spectrum. Okay, so Cardy, based on this operator state correspondence, proposed that this left-hand side should be related to the right-hand side by the following formula. So the first equation relates the energy with the scaling dimensions. So as we can see that it's linear and up to some finite set correction. So this term is the finite set correction, that x is larger than 1, and this term will die off as you have larger and larger system size. And the momentum equals to the conformal spin by 2 pi over n. And here, what we can do is that we can rescale P, and we can rescale E such that the left-hand side equal to the right-hand side. Okay, just let me mention that to rescale E, we need to fix the ground state energy to be 0. And the other thing that we fix is this state. Okay, is this state, which is the blue state here. Okay, the blue state here. We know the exact result in CFT that this state must have scaling dimension 2, and it's called the stress tensor state. So it's exactly conservative quantity, so we know that it's scaling dimension 2. And in the lattice calculations, we can identify this state and fix the scaling dimension to be 2. And in that way, we can fix this A and B. Okay, so you need two quantities to fix A and B, and the two quantities we choose are the energies of the ground state and the energy of the stress tensor state. Okay. But if you follow from this equation alone, the equations alone will only give you a set of scaling dimensions and conformal spins. It will not tell you which state and which state are the same in the conformal tower. And of course, this is expected because to identify conformal towers, you need to know the action of Virasoro generators that connect within the same conformal tower. But Cardy didn't give you extraction of the Virasoro generators. So this is what we did, and of course this is pioneered by Ku and Seller in 1994, and Milstead and Wedal in 2087. And what we did is try to see whether it holds to general models. And Ku and Seller proposed it based on integrability, but we also tested for non-integrable system and find it works. Okay, so let's see first on the right-hand side, the CFT, what Virasoro generator is doing. Okay, so Virasoro generators have two parts. One part is the holomorphic part, which is called Ln, and one part is the anti-holomorphic part, which is called L bar N, and yeah, L bar N. And okay, so let me give you an example of what Ln and L bar N would do. Okay, I already give you examples here, but I want to draw it also here. So, so for example, if you have L-1, it will drive you to the with larger conformal spin and larger scaling dimension by 1. If you have L bar -1, you will go from the other direction, which is scaling dimension up and conformal spin down. And if you linear combine them in a way that Ln is combined with L bar -n, then you can see that in the central figure, in the central of the figure, you see this. So from the central point here, this point, if we will apply H-1, which is L-1 and L bar 1, you get both from the to the right up and to the right down. And also you can see this. You can see also the H1 would act exactly at the same way. Okay, so this is what Virasoro generator does in a CFT, that it connects the state within the same conformal towers. Of course, at the base of this of the whole thing, there's a primary state, and the primary state will connect to all the descendant states up, but it cannot be lowered by this Virasoro generator. So it is the base of the tower. And yeah, so what we did, and also what Ku and Seller did, is that they proposed this lattice Virasoro generators. So you just need to take the Fourier mode of the Hamiltonian. I hope this is clear. So this Fourier index. Yeah. So this Fourier. So this Fourier proportion constant, and you just need to profile this the Hamiltonian term with at each side with different phases, and this is not an accident. So this is not a random proposal. This proposal is based on the fact that in the CFT, the Fourier mode of the Hamiltonian would correspond to these Virasoro generators. So we just need to make a lattice version of it. And indeed, we see that if we really do that, do this lattice operators, we see the H1 and H-1 will exactly do the same thing. Of course, with finite set corrections. Okay, and this already shows that this lattice Virasoro generator work. We also want, apart from H1 and H-1, we also want H2 and H-2. And in this case, I show you an example of what H-2 is doing. So so this is important in the sense that it connects the identity state with the T state, with the stress tensor states. And on the lattice hand side, we can also see that H-2 would connect these two states. And the important thing about H-2 is that the central charge can be extracted from the amplitude in this transition. So by the amplitude, okay, I will be more precise later. Okay, but first let us see what's the whole result of this lattice Virasoro generator. Okay, let's take.
May I ask a question?
Yeah.
So maybe I missed it, but it seems like what we are discussing so far does it require this uniform periodic matrix product state, or just
No.
generic?
No. Yeah. So this is
right?
you take a spectrum. You take any spectrum you want.
Yeah. So the numerical technique and what you're discussing so far is not related. And just to make sure I understand.
Okay. Sure. Okay.
Okay. So the second, I have another question. So, but when you actually do the numerics, I guess you're doing the periodic uniform matrix product state and such and optimize it. And
Yes.
how do you actually numerically optimize it when you don't have a canonical form?
Okay.
For example, how do you know it converges, for example, rather than each oscillatory?
Okay. So we can talk about this after talk. And for here, I will just give you a short answer that optimization problem really does not need a canonical form, right? Like you just take it as a function of energy functional of the tensor, and you do a gradient descent. You compute the gradient. So okay, let me get a little bit back to the measured product state. Yeah, so the energy is also a function of A, right? And you can compute this gradient, of course, by exactly contracting the whole tensor network, not by a canonical form, which you can resort to local into a local form. So this is much harder to contract because you need to contract the whole tensor network. And then you can just use the gradient method to move forward to see that your energy will go down by tracking this gradient direction. That's the short.
Thank you very much.
Yeah, that's the short answer. Okay, yeah, as Sun Wang just pointed out, like the whole thing does not require a measured product state. Okay, the whole procedure of this lattice Virasoro generator is completely general once you get the low energy spectrum, even with exact normalization. And of course, in this figure that I show you, this is n equal to 20, so, which can of course be achieved by exact normalization. Okay. Okay, but just let me show how powerful the whole thing is can be. I will use n equal to 64 instead of 20. It's still very quick. It can be done with 5 minutes, and you can get a bunch of ground state and excited states of the icing model up to level 7. If you count it, it might be over 100 excited states. It's very hard to get by other momentum methods. Okay, and we see that if you okay, let me repeat that the colors on the right hand side is to indicate the numerical identified conformal towers, which are obtained by using the lattice Virasoro generators. And of course, the lattice Virasoro generators also have finite side effect, so you won't see that the left hand side is equals to the right hand side. And for n equal to 64, you already see that they are very much the same in this whole region. They are really the same. You can try to see them, like the whole thing is the same, and the only error occurs at level 7. I believe this is unprecedented. That it's the first time that we can really see this up high. Of course, this is for the icing model, and for other models, it won't be so nice. But still, it shows that by the eigenstates, by the lattice eigenstates on the periodic boundary conditions, even with this small system size 64, you can get a very good approximation of the conformal data. Okay. Okay. So I will show you a list of conformal data in this page. So the first thing is the scaling dimension. okay, the scaling dimension of each state can be obtained by the energies, right? And this is just the precise statement. So you just need to compute the energy above the ground state energy and normalize it with the T state energy. And this is the scaling dimension, and this is the equation that I previously want to talk about. That is, the central charge is given by the amplitude from the ground state to T state by the Virasoro generator x minus 2.
I'm sorry, what was the T state? Just a question. Sorry, what was the T state?
Sorry?
What was the T state? The T state?
Yeah, okay. T state is this state at scaling dimension 2 and conformal spin 2.
Sure,
yeah. Yeah, it's a state that is present in all CFT and is connected by H minus 2 or L minus 2 with the ground state. Okay.
Thanks.
Okay, so with on the right panel, you see a figure, and the figure is not so clear. Let me explain. So the left hand, so the x-axis is 1 over n square. Is going to be an extrapolation, and the y-axis, the central charge computed at different finite sizes, and I believe in this figure what we have shown is n from 64 to 256, and as you can see that we can linearly extrapolate this to n equal to infinity, and this is the result, extrapolated result. And we can do the same thing for scaling dimensions, and this is shown in the lower panel. And okay, so in the table in the left, this is the result that we are very proud of. See this accuracy, and I also okay, just let me a little bit explain this. So as I said before, that the T state here is fixed to scaling dimension 2, so we don't need to extract them. And in other methods, typically you need to compute them. And they get they get a fairly good accuracy, but not so good. And for the low lying states, which are this thing, we also opt for forms other methods. And this other method, if you don't know it, it's fine. Like, they are tensor network methods, and they work extremely well. I mean, like, they are very useful. It's well acknowledged that the tensor network algorithm is the best in computing 1+1D system. So our algorithm is even the best among the tensor network algorithm. So that is a very good hint that's a very good hint of how accurate our method can get into. And of course, the accuracy is due to two facts. One fact is that we can go to larger system size, and the other fact is that we make this extrapolation.
Can I ask a question here?
Mm-hmm.
Do you also know how it compares to finite DMRG, where you just have the periodic bond going through the system?
Okay, yeah. Okay, so for finite DMRG, I would say that it's not a systematic method. By not systematic, I mean that for finite DMRG always work with open boundary conditions, right? So if you have open boundary conditions, you have boundary state that you actually don't know.
Oh, no, sorry. I mean finite DMRG, but for a periodic system.
Okay.
Right, where you just have this non-local bond going through the system.
Okay, yeah. So for finite DMRG, the problem is that you cannot have the momentum eigenstate. So you cannot have exact momentum eigenstate, right? You cannot force it. And the result is that you cannot get so many eigenstates. So remember that in this figure, we can get in the left panel, we can for each momentum sector, we can get like 10 or 20 eigenstates. And I think for DMRG, you can get 20 states. You can get 20 eigenstates, which I guess the accuracy is poor if you go that high, and you cannot get to so many. But in addition, you lose the momentum eigenstate, which means that the conformal spin is not exact. And I think the overall thing, the overall impression is that should be that you can only get like this part, like the whole thing is like 20 eigenstates. So you can just.
I see. Okay, it was not clear to me. You're explicitly conserving momentum in your setup. It's an explicit quantum number that you're keeping track of.
Yeah.
I see. Thanks.
Yeah.
Thanks.
Can I ask a question as well?
Mm-hmm.
So with this large N extrapolation of the central charge and the scaling dimensions, is there any specific reason to think that you should be doing it as a function of 1 over n squared? Because I'd imagine if you did it as a function of like 1 over n, you wouldn't get as accurate of answers.
Okay. So first, let me answer you the second question. If you use 1 over n, you will not get as accurate because it is 1 over n squared. So this has a prediction from CFT. Okay. Yeah. So for in a CFT, we have So for a lattice model, it's not exactly the CFT Hamiltonian, but it's the CFT Hamiltonians from irrelevant perturbations. And these irrelevant perturbations determines the finite set correction. So for the Ising model, the irrelevant perturbation is this one. Is this the irrelevant perturbations is known, like it's scaling dimension 4. So that is why that we can know exactly what this what this power should be. And in other models, of course, this number could be different. But the point is that this number is also universal. This number only depends on. Oh, sorry, I shouldn't say this number is universal. This number is also determined by universal quantities. So for the Ising model, you have the irrelevant perturbation as scaling dimension 4. That's why you have a 2 here. But for other models, you can try to guess what irrelevant perturbations is there, and you can try to guess this power. And of course, this is restricted. This is in a restricted set because this number must be related to some irrelevant operators in the CFT. So so in the Ising model, it's pretty clear that it should be 2, and for other models, just need a little bit guess. Mm-hmm.
Can I ask a follow-up question? Is the reason you got the wrong answer is the irrelevant perturbation why you got the wrong answer for the scaling dimension 7?
Yes. Okay. So irrelevant perturbations is the reason why you have finite set correction, right? So because the left-hand side the left-hand side is not completely equal to the right-hand side to the HCFT. So that's why the spectrum are different, and the difference is exactly what this irrelevant perturbation is doing. So and it can be generally shown that this irrelevant perturbation would have more effect at higher energies than lower energies. So that is why that when you go up and up, the quality becomes lower and lower. Okay.
Thanks.
Okay. Okay. So at this point, I guess everyone should have a hint of how our method is doing. So just let me try to apply it to a more challenging problem so that you see. Okay, so I have the Ising model, and I perturb it by a perturbation, 3 sides perturbation. It is shown that at lambda equal to 0.428, this model goes a phase transition, like goes into a phase transition. So before lambda equal to 0.428, this is a critical line described by the Ising CFT. But and after this lambda star, it becomes a gap theory. At this lambda star, it is a tricritical point and described by another CFT, which is the tricritical Ising CFT. Okay, and if you just focus on lambda equal to this tricritical number, and diagonalize the Lorentz spectrum of this lattice model, and the left-hand side is what you get. And just by applying this lattice Virasoro generator trick, you can identify the conformal towers. And it is very good to see that this is correct, because this primary operator epsilon prime prime is very high up. It's at scaling dimension 7. It's at scaling dimension 3. If you just look at the spectrum, you won't realize that this is actually primary state. But by the lattice Virasoro generators, you can actually see that there are no states lower that can be connected to this state by lattice Virasoro generators. So we identify that as a primary state. And we can also get the all the conformal data, like the scaling dimension and the central charge. And we see that the error is roughly like the order of 10 to the minus 4, 3, 5. Well, it's worse. Sure, it's worse than the Ising model. And the reason is also that we didn't try to get too much system size. So I think the largest system size that we try to get here is like 80. But the only reason that I get to 80 is that I'm lazy. I don't want to wait for larger system size to run. And still we get a very good accuracy. Okay. The other very interesting property of this model is that it has a critical line, which is described by the Ising CFT from 0 to lambda star. And in the field theory language, if you have a lambda star and you perturb it a little bit to the left, like you decrease the lambda a little bit, this is a relevant perturbation because it drives you from the tricritical Ising model to the Ising model. So a relevant perturbation would induce an RG flow in this direction. Okay, and it's interesting that we can actually numerically observe this RG flow. So we choose this lambda to be 0.4, which is very close to the lambda star, which is 0.428. And so in the left panel, I show you what the spectrum will look like when you have very large system size, which is 256. And you see that this spectrum really looks like the Ising model. Of course, there are corrections, but qualitatively, it looks very much like the Ising CFT. Yes, and that is expected because, of course, by definition of RG flow, you should see the IR fixed point when you have larger system size. But if you have small system size, actually you see a lot about this UV CFT. So if you look at the right figure, you actually see that there are 6 primaries identified, and actually this looks pretty much qualitatively the same of the tricritical Ising CFT. So one natural question to ask is that how does these states connect to each other when you increase the system size? So on the right-hand side, you have system size equal to 32, and you can make the system larger and larger, and you can see which states will go to which state of the left-hand side. And this is the investigation that we did. Okay, just let me repeat. We have the Hamiltonian equal to the tricritical Ising Hamiltonian plus the relevant perturbation. And in the CFT, this is known as the epsilon prime perturbation. In the left-hand side, this is the numerical result that we obtain. So we increase our system size from like 20 to like 200, and we see that which state will connect to which state. Of course, we see that the scaling dimensions of these states will go into the corresponding state in the large limit. So that is the spectral RG flow that is actually conjectured long time ago, that people conjecture that if you turn on the relevant perturbations in the CFT, the corresponding operator will flow in this manner. And their conjecture is, of course, based on symmetry considerations. And it's nice that in our numerics that we actually see that. And quantitatively, the spectral flow of the sigma state, of the energy of the sigma state, which is this line. So this line is actually quantitatively computed by integrable field theory. And of course, this integrable field theory is a conjecture, like it is applied to excited state. So so they already noted that it is a conjecture, but it can be quantitatively computed by this conjecture. And our numerical result actually agrees quantitatively with their result. So it's very nice to see that this spectral RG flow can both be computed in an analytical way and in a numerical way. And yeah, of course, the analytical way depends on integrability. So that's not general. So our method can potentially be applied to non-integrable theories, which could help us understand the RG flow better.
Can I just ask here? So I presume for every value of n, you fix the scale with using the stress energy tensor T, like use the T state to fix that to scale dimension 2 throughout.
Yes.
Okay, and then someone can also track the central charge as a function of 1 over n. And like a conceptual question, can you imagine any lattice argument for why this always has to decrease?
Sorry, can you say your last sentence again?
Oh, just hinting at the C theorem. Like, is there some, given that you have this now lattice definition of C, right? Even away from a CFT, could you imagine some general argument that argues it has to?
Yeah. So numerically, we indeed observe the C theorem, and yeah. So I think in general, yeah, in general that if you measure the C quantity, it will give you the RG flow, the C quantity from the tricyclical IT model to the IT model. I'm not sure that this C quantity is exactly the same C quantity as defined in homological. But that C quantity has a very rigorous statement, right? So it is the yeah. So either you can cast it as entropy derivatives or as the TT bar, as the expectation value of TT bar. It's a rigorous statement, and in our case, our C is defined in this way. So I'm not sure that why this C is the same C as the homological C, but still you can observe that this C would decrease from 0.7 to 0.5 in this RG flow. Okay, I will move on to another topic, which is extracting of OP coefficients. Okay, so let's first focus on the right panel. So in a CFT, you have local operators, have CFT primary operators, and you can use a Fourier transformation to get the Fourier mode.
Just to keep track on your time, like would finishing in roughly 10 minutes work for you?
Yeah, sure, of course.
Okay.
Okay. Yeah. So yeah. Okay. So this so you have the Fourier mode of a CFT operators, which will send you between different conformal towers. Okay. And for example, if you take the sigma operators and take the Fourier mode 0, -1, 0, and 1, this will give you this these arrows and also these arrows, which I didn't draw. And on the lattice side, you can take sigma x and also do the Fourier mode, and you can see that it will exactly do the same thing, as the CFT side, and also the amplitude would match. And in the CFT side, this is the OP coefficient, and on the lattice side, you can also compute the OP coefficient from this overlap. And in order to make this general, what we do is that we write the variational ansatz where we expand the lattice operators in terms of a sum of CFT operators. And we require that the left-hand side acting on lattice eigenstates will produce the right-hand side at the CFT state. Of course, there are several technical details that I'll omit, but the key point is that in the end of the numerical procedure, we obtain extension of lattice operators in terms of CFT operators, which is this which is this table, and we can do for this for any lattice operators. So this is completely general. one example is that in the Ising model, you have, if you take sigma x, you find that it has components in sigma and also has some derivative descendants of sigma and also higher up. But if you take another two-side operator, which is xz plus zx, you still get sigma, but you also get another derivative, another proportion of derivative descendants. And if we use x to rescale such that the coefficient of sigma is equal to 1 to extract the OP coefficients, and we get the red line. Of course, the red line is good. It's good in the sense that it converges to the CFT value. So remember that this is a log scale in the difference between the numerical value and the CFT value. And you can actually do better by linear combine x and xz plus zx such that these terms get canceled. So and the linear combination is showing in the blue channel. And you can see that this is not only converge faster, but the final set effect is smaller, significantly smaller. And and indeed this indicates that this linear combination is a better candidate for sigma CFT than sigma x alone. So we can, and the point is still that we can do this for general lattice operators and to arbitrary order if you want. So so that's a very nice correspondence between lattice and CFT. Okay, and just to show you that this not only works for the Ising model, so this is also works for the tricyclic Ising model with, of course, less accuracy. Okay. Okay, so this is what I will skip. And okay, in the last part, I will try to advertise the multipartite entanglement, which I recently did with Mike Zalatel's group. So we want to study the entanglement measures in CFT. So bipartite entanglement measures is actually well studied. Which almost like the entanglement entropy will characterize, like the entanglement entropy will characterize almost everything about bipartite entanglement. This entanglement entropy in CFT is first examined in Wilczek in 1994 and also collaborated with Cardi 2004. And it has a holography interpretation by Yu Takanagi, which is well known. But multipartite entanglement measures are actually very less studied. Like people don't even know how many multipartite entanglement there could be. And in this talk, I will focus just on one, which is the entanglement of purification. This entanglement of purification is defined as following. So take the pure state and divide it into 3 regions, and you get the reduced density matrix. And you can try to purify this reduced density matrix by two auxiliary systems. And we just ask, what is the minimum of entanglement ACL and BCR that we can get by this purification? And this is the definition. Yeah, it's very it's very unintuitive, but just need to take it. And we define the following quantities, which is the entanglement purification, GAB equals to the 2 entanglement purification minus the mutual information. And the reason to subtract the mutual informations is to subtract all the bipartite entanglement in a rough sense. So this subtraction makes it makes a very clear physical interpretation of these G quantities, that G measures how much entanglement cannot be factored pairwise. As we know that for a gap system, all the entanglement are essentially pairwise in a gap system. So G equal to 0. And this can be proved in a rigorous region, in a rigorous manner. And what we care about is what is G in critical system or in CFT. And holography tells that this G should equal to this number because EP is due to some geometric quantities, which is completely determined by central charge. So in the end, if you do the algebra in holography, you get this universal G that they want to show you. Okay, but what we did is we tried to compute this G in lattice models exactly So we get the G's, we get C over 3 log 2 for various CFTs, and we find, oh, okay, they are not the same. So these holographic conjectures must be wrong at small central charge. So, well, it could be that finite N correction is very large, so that this CFT cannot be regarded as a holographic CFT, but still we managed to show that to compute this entanglement measure and show that the holographic conjecture does not hold in these CFTs. Okay.
Can you just ask to exclude the option of the finite size effect? I guess one could do free fermion ED.
Yes. So for this model, you can do free fermions.
Right. And then, yeah, that will be also a benchmark for your method, I guess. Or?
Yeah. So free fermions, we also tested, and it almost give us the same result. Right, it's more accurate, but the first 3 digits are the same.
Okay, great.
Okay, so just let me give you a summary. Sorry, a little bit over time. And so given a Hamiltonian, and we want to know the universal data. And what we do is we try to focus on the low energy spectrum. And by the low energy spectrum, what we can do is we can extract complete conformal data, identify the conformal towers, and the thing I didn't talk about, try to identify emergent symmetries, and also try to compute multi-parallel entanglement entropies, which is actually very hard to compute in a field theory language. So, and this is completely general and potential to tackle more challenging CFTs, which means non-rational CFTs and very large central charge CFTs that we have no analytical capacity. Okay, so that's it.
Great, thank you very much for a very interesting talk. Let me stop the recording now.